Let's look at the next topic. We're on section 4.2, the mean value theorem. Now, even though the section's called the mean value theorem, we're going to first start with Rolle's theorem and then generalize it to the mean value theorem. So remember, this is a little bit different from what we've been doing before. We used a technique to find local max of a function, max or min of a function. We could find exactly what that point was. Here, we're going to be taking an approach similar to the intermediate value theorem's approach, right? Where we're going to be showing the existence of a point or the existence of a solution to an equation, even if we might not necessarily know what that point is. So here's fact 1, Rolle's theorem. If we have a function that is continuous on the closed interval, a to b, differentiable on the open interval, a to b, and has the same y value where it starts as where it ends, then there's some value c in the open interval a to b such that f prime of c equals 0. Now let's think about what that means, right? Because I think we can illustrate this. Suppose we have a set of axes and we start somewhere, maybe there, and we end somewhere there. Now suppose that we start at this value, and I guess we're supposing that we're going to end at that value too, right? We're assuming that f of a equals f of b. Well, no matter what we do, it can be something as simple as this, for example. Well, there's got to be some value, c, where the tangent line is horizontal. Right, so like right there or so it looks like, right? Right there we have c. We don't know what it is. But it's some value right there where the derivative is 0, right? Which we know because the tangent line is horizontal, right? And you don't need to draw this shape, right? You can do anything you want, and you can see there are all these various points where the derivative is 0, right? So no matter what, as long as our function's continuous and differentiable, right, then we've got to have such a point c, right? Now, one thing to keep in mind if you want to use Rolle's theorem, you first have to verify that f is continuous, differentiable, and ends where it starts. So, for example, you might say, well, who cares? How is that useful? Well, here's an example, and this isn't even something in the book. I just came up with this example. Show that this function contains a critical point, right? Now, there are two ways to do this, right? You could go ahead and take the derivative, do that nasty product and chain rule, and set it equal to 0 and try to find when it equals 0. You have fun with that. Or you could use Rolle's theorem, right? Well, first off, I'm going to say let y equal f of x. I should have done that in the beginning, okay? So f is continuous really everywhere, right? Right, just because sine and cosine are continuous, polynomials are continuous, and so their compositions and products are continuous, right? All right, so it's continuous on negative infinity to infinity, so of course it's continuous on all subintervals of that, right? Closed or open, right? So let's see. Also, you can see that f is differentiable on, well, negative infinity to infinity as well, right? We're always differentiable. All right, we're good to go with that. Okay, now let's note, that f of negative 1 equals 0, right? Because if you plug negative 1 in here, then you get that sine of this thing, right, that's 0. Doesn't matter what it is here, the whole thing is going to be 0, right? Because sine of 0 equals 0. Right? Now, similarly, trig functions are periodic, right? That means that they repeat values every 2 pi. So I could also plug in negative 1 plus 2 pi. So I could say that f of negative 1 plus 2 pi also equals 0 because sine of 2 pi equals sine of 0, which equals 0. Okay? Well, how is this helping us? Well, we've shown that f is continuous everywhere. It's differentiable everywhere. And now we've shown that f of negative 1 equals f of negative 1 plus 2 pi. So, by Rolle's theorem, there's some c in the open interval negative 1 to negative 1 plus 2 pi such that f prime of c equals 0. Right? So f contains the critical point. C, comma, f of c. I don't know what it is. I don't know what c is, so I sure don't know what f of c is. But I know that this critical point exists. Okay? That's the proof. So note that this was a proof. I wrote an argument, right? I verified the three components of the three prerequisites of the theorem, and then I used it, and then I got my answer. That's the sort of approach we're going to take in this section. All right, let's look at another example. Show that this equation has at most one real root. Sorry, if it's an equation, then it should equal 0. Has most one real root in the interval negative 2 to 2. All right? So we're just going to let f of x equal x cubed minus 15x plus 5. Okay? So f is continuous and differentiable on negative infinity to infinity, right? And so, of course, it's going to be continuous on negative 2 to 2, differentiable on the open interval of negative 2 to 2, right? You can just sort of say it. If you know it's continuous and differentiable everywhere, then you can just say that, okay? And now at this point, we're going to do something a little bit different. We're trying to show that f has at most one real root. Now, one way to prove something, this is very common in mathematics, is called a proof by contradiction, where you assume the opposite of what you're trying to show, and you show that this assumption leads to something that's obviously wrong. So I'm going to say prove by contradiction. Suppose f has at least 2 real roots in the interval negative 2 to 2. Well, then that's going to give us, or maybe I should just say, i.e., assume f has roots R1 and R2 such that f of R1 equals f of R2 equals 0. Right? Okay, well, we've assumed that, okay? So we've shown that f is continuous and differentiable everywhere, and so including on this interval. We've also shown that we're assuming, I should say, we haven't shown, but we're assuming that f begins and ends at the same y value, right? Just by assumption, right? If R1 and R2 are roots, then f of R1 and R2 have to equal 0. So we can say, by Rolle's theorem, there's some c in the interval, actually I guess it's the open interval, negative 2 to 2. Now, I could have chosen any interval for this, but because we're interested in this interval, right, I'm going to do this, right? I could have just changed this, I could have just changed this to, you know, the open and closed intervals of -2 to 2. Right, but there's some C in this interval in particular. All right, no, sorry. I guess I should say we assumed that R1 and R2 were in this interval, right? So we're good to go. So anyway, there's some C in that interval. You know, actually, sorry. Let me be clear about this. I apologize for that. Let me go all that. All right, so that there's some C in the open interval from R1 to R2. That's what we're assuming. That's what we're assuming. Okay. Some C in the interval from R to 1, 2, such that f prime of C equals 0. But f prime of C equals, we can just take the derivative, right? Right? So you see that we're assuming this and this. Like actually, let me say, we're computing this, but assuming this. Right? Okay. So let's keep doing this out. 3 times c squared minus 5 equals 0 implies 3 times c minus root 5 times c plus root 5 equals 0. But the problem is, oh my goodness gracious. Sorry, there's a thunderstorm going on out there. So c equals plus or minus root 5, which is a problem because plus or minus root 5 is outside the interval -2 to 2. So we have a contradiction, right? We assumed that we had C in our interval from R1 to R2, and that this was in turn contained in -2 to 2. But then we showed if that's the case, then it has to be outside the interval. So our assumption was wrong. So f has at most one real root in -2 to 2. Okay. So this is a bit of a challenging argument, right? It's an argument, right? We didn't do a whole lot of math. We made an argument, right? We assumed the opposite of what we were trying to show. We used Rolle's theorem, and then we actually just, here's the one piece of calculus we did, right? We took the derivative, and then we got a nonsensical answer. And that's called a proof by contradiction. Now, I don't know if example 3 seems familiar. You'd have to think a while back, but we used the intermediate value theorem to show that this equation, again, it should equal 0, has at least one real root in the interval -2 to 2, right? So before, we used the intermediate value theorem to find a lower bound for the number of real roots of an equation. Now we use Rolle's theorem to find an upper bound for the number of real roots. So the conclusion is x cubed minus 15x plus 5 equals 0 has exactly one real root in the interval -2 to 2. All right? So let's look at example 4, and I just pulled this right from Stewart. Show that this equation has exactly one real root. Well, I'll tell you right now, you're not solving for x there. There's no technique to do that. You can plug it into a calculator. It'll give you a pretty good limit, pretty good approximation, but it's not going to be anything obvious. I don't think it's anything nice, right? So what you have to do is you have to say, okay, hold on a sec. First of all, we're going to let f of x equal 2x plus cosine of x. Okay. So f is continuous and differentiable everywhere. All right. So now we're going to do the same thing we did last time. This will be a little bit easier than the proof last time. Actually, I should say, first off, because they said exactly, we have to show two things, right? We have to show that it has at least one real root, and then it has at most one real root. Okay? So we'll say show f has at least one real root. I guess we can just say, since f of, I'm trying to think of a number that's clearly so I guess we said since f of -1 equals -2 plus cosine of -1, which whatever that is less than 0, right? Because the cosine is bounded by -1 and 1. And f of 1 equals 2 plus cosine of 1, which is greater than 0. By the intermediate value theorem, there's some c in the interval from -1 to 1 such that f of c equals 0. So f has at least one real root, right? This is intermediate value theorem stuff, right? This is way back in section 2.5. Okay, let me just point this out, right? This is at least one real root, right? Now, actually, maybe I'll use blue for this just so that it pops, right? Show f has at most one real root. So at this point, we know already, again, that f is continuous and differentiable everywhere, right? So all we need to show is, we'll just say, assume f has two real roots, R1 and R2. So f of R1 equals f of R2, which equals 0. It doesn't matter that they equal 0. It just matters that they equal the same thing. By Rolle's theorem, there's some c in our interval, our open interval from R1 to R2, such that, well, what do we know? F prime of c equals 0. But, well, what do we know about f prime of c? F prime of c, by definition, equals, where's the 2x? It's going to be 2 minus sine of x, which is greater than 0. Do you see that that's a contradiction? On the one hand, Rolle's theorem says that if we assume that there are two real roots, then we have a derivative that equals 0. But we also have that f prime of c is greater than 0 for all values of c. Right? It doesn't matter what c is. I'll say this is a contradiction. So f has at most one real root. Right, see, this is at most one real root. Right, and so you see how we have at least one real root and at most one real root. So f has exactly one real root. Okay, so that's that. So we've done a couple of Rolle's theorem problems, right? That's the kind of thing I could give you on an exam. We're not going to have a quiz on this, but that's the kind of thing I could give you on an exam. We're going to generalize this a little bit, right? Before we had a curve that maybe looked like this, and we said, aha, there was a tangent line there, right? And if you think about it, what we were really doing is you were saying it's parallel to this secant line right there. We're going to generalize that concept. Remember that the average velocity of a function is the value of the secant line, or the slope of the secant line. It's going to be f of b minus f of a all over b minus a. Right? The slope of the secant line from a f of a to b f of b. Now to illustrate that, what's going on here, right, if we've got some values, maybe this is a and this is b, right, and maybe, I don't know, maybe f of a is down here. Now here we're assuming, unlike Rolle's theorem, we're assuming that we don't necessarily start at the same value, right? Whatever our curve does, maybe it goes like, ooh, something like that. I don't know. Right, that's y equals f of x. Well, and let's just note our secant line. Let's see if I can draw a nice smooth secant line. Right there. And you see that has slope. Right, that's the secant line with slope f of b minus f of a all over b minus a. Well, what they're saying, right, what the mean value theorem says, and I'll write this out in a second, is that there's got to be some c. Looks like it's right there in this case, such that f prime of c equals the slope of the secant line. Okay. So the mean value theorem says if f is continuous on the closed interval a to b, differentiable in the open interval a to b, but we don't need to assume that f of a equals f of b, and there's some c in the open interval such that f prime of c equals the slope of the secant line. So in other words, there's some value c where the instantaneous velocity of f at c equals the average velocity on a to b. So again, another example. All right, so here we've got our secant line. There's some value, maybe here it's like here or so, right, where the derivative of the curve is exactly, actually I guess that's, maybe it's more like here then, where the derivative of the curve is exactly equal to the slope of the secant line. Right, and so f prime of c equals the slope of our secant line. Right, so that's what we've got. Now remember, if we ever want to use this theorem, then we have to verify its conditions. So here's a nice little example. I once heard, and I like to use it, right? Suppose that we're driving in a car, we pass mile marker 100 on a road. And maybe there's a little camera that takes our picture and says, okay, you passed mile marker 100 on the road, and it notes the time. And then 2 hours later, we pass mile marker 260. And at that point, a camera takes another picture of us, and then a police officer pulls us over and says, hey, you've been speeding. And he said, no, I was going the speed limit when you pulled me over. The police officer said, yeah, but you drove 160 miles in 2 hours. The speed limit is 65 miles an hour. And you say, yeah, but you don't know exactly when I was speeding. You don't know that I was ever going over the speed limit. But they could say, yeah, but using the mean value theorem, I know there had to be some point where you were going above 65 miles an hour. Let's take a look. All right. So we'll say let f of t equal car position at time t. So f of 0, we'll just call this f of 0 equals 100, and f of 2 equals 260. Right? So our car has average velocity we'll say f of 2 minus f of 0 over 2 minus 0, right, which is the same thing as 260 minus 100 all over 2, which is 80 miles per hour on the interval from 0 to 2, right? That's our average speed in those 2 hours is 80 miles an hour, right? Since f is continuous on 0 to 2 and differentiable on the open interval from 0 to 2 by the mean value theorem, there's some c in the open interval from 0 to 2 such that f prime of c equals f of 2 minus f of 0 all over 2 minus 0, which we said was equal to 80 miles an hour. So the officer says, look, you traveled 160 miles in 2 hours. Your average velocity was 80 miles an hour. By the mean value theorem, there had to be some moments in that 2-hour stretch where you were driving exactly 80 miles an hour. So that's above 65. So I'm giving you a ticket for going 80. Now, when did it happen? Well, we're not exactly sure, but we do know that it happened. So at some point, you hit 80 miles per hour above the 65 mile per hour speed limit. So that's just a nice, cute little application of the mean value theorem. Now, you might be saying to yourself, oh, that's pretty silly. Come on, no police officer does that. No, but that is how radar guns work. Radar guns don't literally find your instantaneous velocity, right? That's not literally possible. But what it does is it takes a picture of your car at one moment, and then very quickly afterwards takes a picture of your car. Again, maybe it's like over a second or something like that. It takes one picture, and then a second later it takes another picture. It then calculates the average velocity that you were traveling in that 1 second. And then, using the mean value theorem, says, hey, if your average velocity was over the speed limit, then at some point you were going exactly that speed and you were speeding. So let's see. So now let's just go to this is just sort of a more conceptual, tricky problem. This, I just pulled this right from Stewart, right? Suppose that we have a function whose derivative is between 3 and 5 inclusive for all x. Show this bizarre inequality, right? So, yeah. I guess one thing you could say, one thing you might want to note is that we don't even know what f is, but we know that if its differentiable, if its derivative is between 3 and 5 everywhere, then it's got to be continuous and differentiable on negative infinity to infinity. Right? So we can use the mean value theorem. So by the mean value theorem, MVT, there's some c in the interval. I guess it's going to be 2 to 8, right? Because that's what that's the interval we're interested in, I guess, such that f prime of c equals f of 8 minus f of 2 all over 8 minus 2, right? That's the mean value theorem, right? Right, and I guess we could simplify this to be, again, we don't know what f of 8 or f of 2 equals. We can have it that it's equal to 6, right? Right, 8 minus 2 is 6, right? But hold on a second. We know by assumption that f prime of c is between 3 and 5. So if we multiply by 6, $18 is less than or equal to f prime of c, which we don't even care about, or 6f prime of c, which we don't care about. F of 8 minus f of 2 less than or equal to 30, right? We just multiplied this and this by 6, and this by 6 to get our answer. And look, that's exactly what we wanted. So we're done.